In this video we shall start discussing normal forms. We have to emphasize that usually most people understand lower normal forms easily. Speaking about higher normal forms, about 10% understand them at once, and I really hope that you are here. Some people understand them after several years of experience, and alas, some people never understand them. Sorry, but that's the truth. So once again, I hope you are here and will understand all those normal forms easily. And once again, that extremely important fact that any relation variable may or may not be in any normal form, and it depends on subject matter only. It is if subject matter rules change, any normal form may or may not be violated for any relation. So please absolutely remember this fact. Once you forget that fact, you may not understand any normal form at all. Before we begin reviewing normal forms, let's make a quick review of their definition. Normalization is a process of decomposition of relation variable into projections such that the join of those projections is guaranteed to be equal to initial relation variable. Each of those projections are needed in order to provide that initial relation, and at least one of those projections is at higher level of normalization than initial relation variable is. There are a lot of normal forms: canonical, non-canonical needed as intermediate steps, object normal forms, and so on. Of course, we shall concentrate on canonical normal forms and we shall mention zero normal form. As long as even canonical normal forms bring us a lot to discuss, we shall divide our discussion into 3 videos. We shall start here, then we shall go here and here. The first and the worst state of any relation variable is so-called zero normal form. So a relation variable is in zero normal form if it violates any higher normal form's requirements. So it's not in any normal form, something like this. Yes, this is non-canonical one, but it is a good start point for any further discussion. So that's all for zero normal form, and we shall switch to the first normal form. The first normal form states that a ReLVar in every tuple should contain exactly one value for each attribute, or in other words, every value must be an atomic one. It must not be multi-valued or compound. Let's see how it works. All you see in this picture is violation of that first normal form. So this is multi-valued attribute. You see several marks for a student placed inside one table cell. So how can we quickly calculate average mark, minimum mark, maximum mark, and so on? We cannot, because DBMS has to extract and parse that values somehow, and it all takes a lot of time. The second situation is when we have, for instance, an address and all components like city, street, building number are placed into one table cell. If, for instance, we have to find out all addresses with certain street, how can we do it quickly? We cannot. And the worst situation, a table within a table. That's the combination of multi-valued and compound attributes. So this situation is really the worst, but nevertheless some DBMSs will allow you to create such a decision if and only if you absolutely sure what you are doing and you absolutely have to do it. Otherwise, and this and this and this are mistakes. So how to correct these mistakes? With multi-valued attributes, you should decompose the initial relation into several relations, leaving, for instance, information about students here and placing information about marks here. And you see that now each cell, each row and cell contains one mark only. So all those questions about minimum, maximum, average mark may be quickly resolved by DBMS. If you have a compound attribute, first you have to split it and put in several columns, in several attributes. And in real life, of course, these columns should contain foreign keys, and information about cities and streets should be put in different relations. But the first step is just to split the initial value into several attributes. But speaking about compound attributes, we should once again emphasize that atomicity depends on subject matter only. Let us ask the following questions. Shall we store in separate fields the phone number and the operator code or prefix, the email parts like username and domain, date parts like year, month and day, time parts like hours, minutes, seconds, milliseconds, document ID parts like passport series and number? Shall we or shall we not? It depends on subject matter only and only. In some cases, we shall leave all those information in one cell or one column. In other cases, we shall split it. The decision depends on subject matter requirements only. There are no general, universal, absolute rules here. Subject matter is the only source of information. So here's a brief conclusion on the first normal form. Most DBMSs will not allow you to store a table within a table, so that's good. Each multi-valued attribute should be eliminated by moving it to another relation. And each compound attribute first should be investigated for is it really is compound, and if so, it should be split into several atomic attributes. And further, those attributes should maybe become foreign keys. The second normal form has two definitions, weak and strong one. Let's begin with the weak one. So, a relation variable is in second normal form if it is in first normal form, and every its non-prime attribute is fully functionally dependent on the primary key. The primary key is the main idea here. Strong definition says that relation variable is in second normal form if it satisfies the first normal form and every its attribute is fully functionally dependent on any key. So, primary key here and any key here. That's the main difference. Let's review both situations. This is a violation example of weak definition of the second normal form. Imagine we have information about students' groups, and there is the following rule, that each group has a number within a year. So you may see that for 2000, this is the first, this is the second group. For 2008, this is the first, this is the second. Okay, so we may see that years are not unique, numbers are not unique, but combinations are unique. That's why we have compound primary key here. And there is also a rule that how many years a group should be studying depends on the year of the education beginning. So this information depends on the year only, but not on the group number. And that's why we have partial dependency on primary key. That's violation of the second normal form. Speaking about strong definition, we may see the following situation. The same group, but now it has surrogate primary key, so this combination is alternate key here. And we see that information about how many years should a group be learning also depends on the start year only, but not on the group. Here we have a partial alternative key dependency, and that's violation example of the second normal form in strong definition. One may ask, what's wrong with this partial dependency? The answer is simple. What prevents us from putting 5 instead of 4 here? Nothing. Or what preventing us from putting 99 instead of 4 here? Or 1 instead of 5 here? Nothing. But once we eliminate that dependency, we will guarantee the absence of such mistakes. Let's see how can we do it. So all we have to do is split the initial relation into two new ones. And this is the information about education length. All we have to do is put correct value just once. Since we have know that value, those 5s, those 4th, and so on here, we absolutely cannot make a mistake putting something like 99 instead of 5 or anything like that. So this is good situation. So this is a short conclusion about second normal form. Always try using strong definition and find partial alternate key dependencies that will improve the quality of your database a lot. Then, each attribute that is partially dependent on alternate key should be moved to another relation. And that part of alternate key the moved attribute was dependent on should become the primary key of that new relation. And we shall continue discussing normal forms in the next videos.